I would like to go over this together. Nobody got 100%. Okay, there was one question that I think everybody got right, but most of them, some proportion of people got wrong. So I want to talk through them a little bit, and then rather than doing corrections, I'm going to give you guys a retake, because there are enough problems in the question bank that are like this that I can give essentially the same test, but with slightly different problems, just covering the same things. So that's what I'm going to do. I'm in the middle of building it right now. But it should be ready by tomorrow. So I want to go through these questions, and then I have an exit ticket for you for the cycles, the enthalpy cycles. But before I give you that, I want to make sure that I answer any questions you have about those problems. If there's things that you are still not picking up on with the enthalpies of formation and combustion, and or if you wanted to go over something with the Born-Haber cycles. But we're going to do this first so that you all have this in the bag and know what you need to practice with or figure out before doing a retake. It'll be like any other retake in any other, well, hopefully any other class. If you take it and you get a lower score than you did this time, I will always take the higher score. Okay. So this first one, I think threw a lot of people off, and I think this is also where there was confusion about the Born-Haber cycles yesterday, because this concept of just the distances being an amount of energy, the absolute value of it, doesn't matter if it's going up or down. We have this essentially distance in the graph that stands for an amount of energy. So this is a typical energy diagram, right? Reactants, products. We've got the activation energy hump in the middle. We're going to talk more about that in the next unit. So the question is, what is the delta H? Okay. So the delta H, the change in enthalpy for any reaction, right? What if you just had to say what is a delta H for any reaction? How could you describe it? Like it's a change in enthalpy. What are we comparing in that change? What are we looking at the change from? We're using temperature to eventually calculate that. But if the enthalpy is on our y-axis here, and we're asking what is the change in enthalpy for the reaction, what are we looking at? Where is the change happening? Yes? Okay, yes. So enthalpy at the beginning versus enthalpy at the end, right? So the change is going to be, and Ella, I don't know if you wanted to add something to that. Right. No, that's exactly it. So both of you together, are coming together to say the enthalpy at the end versus the enthalpy at the beginning. Okay? Products versus reactants. Okay? So on this diagram, the enthalpy of the reactants would be where? Like where on this diagram, just describe to me where I would put my pointer to say, here's the enthalpy of the reactants. On the left, yeah. So right here. Oops. So here is our enthalpy of the reactants, okay? This doesn't have a x-axis, but if there was an x-axis, or if you had to draw or write in an x-axis, it would be something like reaction progress, something along those lines, right? So here are our reactants, and then our products are going to be here, right? So when we're talking about the delta H, whether we're thinking about it just in general or thinking about it in terms of the energy diagram, it's the difference in enthalpy between those two, okay? So if you had to pick one number, what number would you pick? 1, 2, or 3? To indicate the enthalpy of, 3. Okay, so this here is our delta H, okay? The question didn't give you the opportunity to say just number 3, okay? It wanted you to imagine that you don't have that value and you're calculating it, all right? So it's asking you to subtract 2 values to get to that value. So what are we going to be subtracting in order to get number 3? 1 minus 2, right? Because 1 is this whole thing, minus this part gives us this. And that's the same idea as what we were talking about yesterday. So maybe for some of you who might have answered this wrong, maybe it makes more sense now that we did the thing yesterday, or maybe this helps make yesterday make a little bit more sense. If not, you can always come see me. Or, we can talk about it. So that's, so this is 1 minus 2 is what we're looking at. We're going to talk more about these diagrams again in the next unit. Okay, number 2, a lot of people got this wrong because they missed a very important minor detail in the question. If you got it wrong and you're looking at it now and you think you know what that minor detail is, or if you got it right because you caught that minor detail, what is the minor detail that was critical to answering this correctly? Yeah, this versus this. Okay, so this is joules per gram Kelvin, okay? But they want it in kilojoules, okay? Which is why a lot of people answered A, which would be correct if they were asking for it in joules, but they were not asking for it. Or sorry, a lot of people. How did I? No, yes, a lot of people answered A. Sorry, I was forgetting this was number 2, which would be correct if the answer was asking for it in joules. That's perfectly set up. We've got our mass. And it's the mass of the water that we care about on top, right? They didn't actually confuse you with that, which is nice. So this is the mass of the water. This is our heat capacity of the water. And this was our delta T, right? The 0.25 grams was the mass of what we burned. And the 46.08, which I put up in during class, or mentioned it during class, and I'm sorry if you didn't catch that. This is the molar mass of the ethanol. So this was basically the mass divided by the molar mass would give you the number of moles. This is the heat divided by that would give you the change in enthalpy. Technically, it should really be negative. There should be a negative sign there. But I guess that wasn't an option in any of these, okay? When we are looking at, it says rise by that much. So that is our delta T. We do not have to convert that into Kelvin because the change in temperature, whether we're looking at temperatures measured in Celsius or temperatures measured in Kelvin, is going to be the same. The scale is the same. So the change is the same. If you already have your delta T, you don't have to change it into Kelvin, okay? So we needed to do the joules, change joules into kilojoules, and that is how we do that by dividing it by 1,000. So if we took A and divided it by 1,000, we would have B, right? Okay, so, and they will mess with you like this. They will do it. So you have to pay attention to the units. All right, this one, I guess we didn't spend enough time on. I was sort of surprised at how many people got this one wrong. But based on that, I think that's me not spending enough time talking about this. So bond breaking, if we are breaking a bond, are we going to have to put energy into that, or are we going to get energy out of it? Is it going to take energy to break the bond? Yeah. Okay, so think about it in terms of, it's a little bit harder to think about gaining energy when we make the bond, but breaking the bond takes energy. The stronger the bond, the more energy it's going to take, okay? So bond breaking has to be endothermic, okay? And that's then knowing whether delta H is positive or negative that's something that you have to know. And you can sort of think about drawing yourself a little energy diagram and say, okay, we're breaking all of the bonds. So this is our reactants. This is our individual atoms. And then we're forming our products, right? So this is going to be a positive delta H, and this is going to be a negative delta H because it's going down. So thinking about that positive, negative as both putting energy in or going up in the energy diagram, and negative being getting energy out or going down in the energy diagram. This is going to be C. Okay. There is, if you want to think about sort of how the how bond forming is exothermic, let me actually pull up that simulation real quick, because I don't think I showed it to you guys. I've showed it to honors. All right, so this is if you were with me, you may have seen this in honors chem. The idea here is just to talk about what is covalent bonding actually doing. I'm just going to walk through this real quick because the slide I want to get to is a little bit later. But the idea here is that they're sharing electrons because those electrons are attracted to the nucleus of the other atom, if we're talking about hydrogen here. If we pull the atom far enough away, there's not enough attraction to form the bond. As soon as we get close enough, then we are going to form a bond, but we can't get too close, or we're going to push the other atom away. Is it going to let me do this? Okay. Yeah. Blah, blah, blah. Okay. Oh my God. Sorry. I should have set this up earlier. Yep. Yes. Okay. This is what I'm looking for. So if we take two separate atoms, not bonded together, just neutral atoms, there's a certain amount of potential energy contained in both of these atoms. As they get closer together, we start seeing that energy go down until we reach the point where we're close enough to form a bond. Then, if we try to get closer, the energy goes back up. Okay? So there's this dip in potential energy. That is the energy we're getting back from forming bonds. Okay? It's the difference between not having a bond and having a bond. That is the bond enthalpy, basically. The reverse of the energy that it takes to break them apart. Okay? And where the trough is here is going to be the length of the bond, the distance where those atoms are going to sit relative to each other. So that's the energy. That's why making bonds is exothermic, releases energy, because that energy, when it goes down here, it has to go out somewhere. So anyway, that's maybe more than you needed to know, but just to make that clear. Okay. I think everybody got this right, or almost everybody got this right. So good job with the Hess's law. All right, you guys rocked it. So I don't really have to say anything, but basically, you needed to look at each one and say, our CS2 has to be on the reactant side, and here it's on the product side, so this one had to get switched, which means this is going to be negative. And then our SO2 and O2 had to be doubled here. So this had to be times 2, which meant this had to be times 2 in order to match that equation. So that is why it's delta H1 plus 2 times delta H2 minus delta H3. So this is D. But like I said, you guys got that. And we'd only really talked about it for a day and a half, so congrats on that. Okay, this, I think that for some people, and again, this is on me, a little bit of the wording may have thrown people off. Like, what's an alkane? How do I know what an alkane is? It doesn't matter what it is, because you're being given a number of moles of a substance that is being burned, okay? You're given a delta T. We're raising the temperature by 57.3 degrees Celsius. So this is our delta T. So we're raising the temperature. That makes this the change in temperature. We've got a mass, right? And then water, we know, is 4.18, okay? So we can get the enthalpy of this by using our Q equals MC delta T and then dividing by the number of moles, okay? So I guess you're going to learn what an alkane is. So if you get this on the test, you're going to be like, oh, an alkane, right, okay. It's a hydrocarbon. It's a type of hydrocarbon. We're going to talk about it when we do the organics unit, okay? Thank you. So you won't be fazed by seeing that word on the test when you get to it. But there may be something in a question that you haven't seen before. You don't know what it is. That is going to happen. I guarantee it. There's going to be things that we don't cover every little bit of something, or you've forgotten what's a word or something like that. So I guess my point here is, even if you don't know exactly what's going on, try to see what are the things that you're being given and see if you can make something of that. And you can use the equations in your data booklet to help you. If you can identify what these different things are, then you can look at the equations that you have and say, where can I put these all together and solve for something, okay? So you're going to have your 20.0. Yeah, so this is the Q equals MC delta T. So that's your 20.0 times your 4.18 times your 57.3, okay? And that's going to give you some, and some of you did this all in one. And honestly, I don't, do I have it here? Yeah. Yeah, so 4790 joules, okay? That is the heat that is absorbed by the water, right? And this is the key to any question where you're using Q equals MC delta T. You have to be thinking about where is the heat going and what is the delta H that I'm actually trying to measure. So this is heat absorbed by the water. And some of you annotated this, which was nice. Which means we have negative 4790 joules released by the burning. Okay. But molar, and it specifically says molar enthalpy, and it gives us the number of moles. So we have to take that number and divide it by how many moles we burned. Okay. You might have a mass here that you have to convert into moles, like in the previous multiple choice question. But here they're giving you the moles, so we just take that divided by 8.75 times 10 to the negative fourth. Some of you dealt with the scientific notation by figuring out what this was in decimal notation and punching it into your calculator that way. Great. If you're not going to do that, which is also great, make sure that you know how to enter that in, because there were a few situations where people had this perfectly set up, but the number that came out was just wrong. And I think it's a calculator error issue. And I'm happy to go over that with anyone or with everyone at some point, how to deal with that. But you would end up with negative 5470 and kilojoules. Now, so you could, if you did this, you would have gotten something like 54,700,000 joules, okay? Because this is in joules per gram Kelvin or degrees Celsius, okay? So if you got that number, if your answer was this, then that's correct, and that would be acceptable, okay? Or some version of this. I didn't take off for sig figs, okay? If you converted it to kilojoules by dividing by 1,000, and your answer was this, that was also correct. Sorry, this should be negative. That either of those was accepted, or any version of that in any units where that was the right number. Yeah. Sure. Let's do that. So it's 10 to the negative fourth, which means we have a small number, which means we're moving the decimal that way, right? So we're going to move it 4 spaces. 1, 2, 3, 4. Here's our new decimal point. We fill in with zeros. So that would be the decimal notation for that. Unless it specifically says in the question in kilojoules or in joules. So that's one of the things you have to look for in the question. If it doesn't specify, then it doesn't matter. Yeah. Actually, sorry, this should be also moles to negative 1, moles negative 1. Yeah. So it's hard. All right, I'm not going to lie. It's hard, and when you get to the exam, it's going to be even harder because you're going to have, all these topics, all these different topics, all pulled into one set of questions, and you're going to have to figure out which one's which and which calculation to use where, and that's hard. So I guess my biggest suggestion is to annotate the questions as much as possible, circle any units, or underline or star or whatever you can do to kind of set off the things that you have. I did see some folks also kind of took all the numbers out of the question and listed them with their units. That can also be a great approach. So you say, okay, I know I'm going to be using Q equals MC delta T here, so I'm going to say, all right, M equals, all right, which M am I looking at? Well, there's only one M here, so 20.0 grams. C equals, well, what is C? Oh, I'm looking at water. So that's going to be 4.18, right? Delta T equals 57.3. Q equals question mark. That's what I'm solving for. So if that's helpful to you, that can be another way to deal with questions that have lots of numbers in them. And can potentially help you kind of identify what equation you might need to use. Okay. Okay. I'm not going to give you that exit ticket today because you don't have enough time. Anything else on this that you would like, that you're still not sure about? Any questions on the cycles packet that you would like me to go over? Yes, Jacob. Question 7, this is in the triangle cycles practice, or the, okay, yep. Let me just pull that up real quick. I know I have it in another slideshow somewhere, but open recent files. Question 7. Okay. I'm going to briefly remind you that you don't have to use these cycle triangle things. There is going to be a question on your exit ticket that is the only one I could find in the question bank that uses one and has you sort of evaluate it. But hopefully that'll be pretty straightforward. But it's literally the only one I could find. And don't forget that you have those formulas in your data booklet for enthalpy of formation and enthalpy of combustion, using those to calculate enthalpy of the reaction. Okay. So this is question 7, and our reaction here is the one of interest, the one that we're trying to find the enthalpy, change in enthalpy of. So what can you tell me about the direction of the arrows? What is the direction, Jacob, what does the direction of the arrows tell you? It will eventually tell you the sign, but what kind of information are we going to be using here? Because the arrows are pointing up. Formation, yeah. And that's, you can also get it from the fact that that's what you're given, is enthalpies of formation. And that's also something, if they don't give you the data and they tell you to look in your data booklet, formation and combustion are in separate data tables. So if it says section 13, it's formation. If it says section 14, it's combustion, or whatever the numbers are. You'll be able to see that. But yeah, we are forming these things. So what are we forming them from? What are we starting with in order to form our reactants and our products? So this is basically saying, write me an enthalpy, or write me a reaction showing the formation of NH4Cl, right? Because we're going from something to create that. So what are my starting substances here? If you think about the definition of enthalpy of formation, what is that? The enthalpy of formation of 1 mole of something from yeah. Right. Sorry. This is going to be elements in their standard states. So I need each of these elements in its standard state. What is the standard state for nitrogen? How would I write it in a chemical equation? Yeah. N2. It's one of the diatomics. What about hydrogen? H2. Uh-huh. What about chlorine? Cl2. Yep. Now, if I'm writing this, if I'm being asked to write this for, if I'm just writing this cycle for myself to figure out this problem, you don't actually need to figure out what to put in this box. Okay, if you're just using this as a tool, it doesn't matter if this is a balanced equation or not. Okay, this top one has to be balanced, but this doesn't matter as much. But you might be asked to write an equation for the enthalpy of formation of this substance. So knowing how to do that is going to be important. So what coefficient am I going to put in front of my N2? Yeah. 1/2. Because there's only one N here. I have to put 1/2 N2. What coefficient am I putting in front of the H2? Yeah. 2, because I have H4. And what do I put in front of the Cl2? 1/2. Okay. And that's true if you're, being asked to do something with multiple products. I haven't seen any questions where they ask you to do formation for something that has multiple products. It's always just one substance. So, but it's the same thing. It's the same thing. It's the same number of atoms, right? So this is then going to be our delta HF of our NH4Cl, because that's the energy that's going to take to go from here to here, right? And then we're going to need to go this way to find to use these numbers for the enthalpies. So this is going to be subtract, and the other side's going to be add. Or sorry, the other way around. Sorry, I'm thinking of this backwards. This is going to be add because the arrows are going in the same direction. And this is going to be subtract. Okay. All right. So tomorrow I'm going to give you guys a warm-up with a couple of cycle questions to kind of get you started, and then we'll do that that sort of mini formative when we get here tomorrow.